I'm very glad to be here. It's my first GSI conference. So yeah, this will be about shape space in one way. It's not clear from the title, but you will see. Maybe it's clearer from the image actually. This is joint work with Boris Hessin, the University of Toronto, and Gerard Michiolek at Notre Dame University. Okay, sorry. So as most of the things we do, this story starts with Newton, and then it goes on to Euler, and then there's a big leap to Arnold, 1966, where he discovered that Euler's equation for an incompressible fluid can be described as a geodesic equation. So in the yellow field there, you see the Euler equations. And they give you, the solution to the Euler equations give you a time-dependent vector field. If you integrate this vector field, you get a diffeomorphism. And that diffeomorphism, a time-dependent diffeomorphism, and that will fulfill, that will be a geodesic with respect to a certain L2 metric. So that was observed by Arnold in 1966, and since then, this has grown into a field of mathematics that is called geometric and topological hydrodynamics, and many equations in mathematical physics have been shown to fit into this framework since then. Kamasa-Holm is one, KdV equations, and so on, so on. There are several. Furthermore, these observations by Arnold, or discovery by Arnold, has led to very nice analytical results, for example, concerning stability of fluids and also concerning short time existence of solutions to these equations. Okay. So what we want to do now is to just continue in this fashion of Arnold, but to extend the framework to look not only for geodesic equations on diffeomorphism, but also for Newton equations. So what I mean with this is you have a Riemannian metric plus a potential function. So that's the case we're interested in. So we have a Riemannian metric, we have a potential function, which is just a real valued function on the infinite dimensional space of diffeomorphism of some compact manifold, which I denote M. And then we assume certain things. We assume that the metric we have is invariant with respect to volume preserving diffeomorphism. And we also assume that the potential function is also invariant with respect to the same subgroup of volume preserving diffeomorphism. So mu here is the reference volume form on the manifold M. So this, of course, is what leads us to shape space, because now we have an invariance, so we can quotient out this symmetry and see what we get. Right, okay, so here is just, if you write down the geodesic equation for a specific choice, the most natural choice of L2 metric, this is how the equations look like. And U bar here is a functional that is induced by the potential functional U. You will see that a bit later. So just to show you some equations. Okay, so the first sort of way to describe this is in terms of Riemannian geometry. So let's start with that. So we have our infinite dimensional manifold of diffeomorphisms. By the way, I'm not going to discuss any issues of analysis in this talk at all. It's just geometry. And this infinite dimensional manifold is a group. It has a group structure. So if you compose two diffeos, you get another diffeo and so on. You all know about that. So that means that there's an identity element somewhere. And if you now take a mapping, pi, which takes your diffeomorphism and acts by push forward on your reference volume form, that gives you a projection, right? And that's projection down to probability densities. So assuming that the volume form has total volume 1, which I will assume throughout this talk. And in fact, it's a little bit more than that, because this projection corresponds to principal bundle. So in fact, if you quotient diff m by diff mu, you get exactly the probability densities. So this is a result by Moser from 1965. So it has been known for quite a while. Okay. So that's just, let's say, the There's no Riemannian geometry yet. Now we want to introduce some Riemannian geometry. So we introduced this L2 non-invariant L2 metric on the space of diffeomorphisms. This is not, by the way, the right invariant L2 metric. It's not going to be right invariant. It's only invariant with respect to the volume preserving diffeomorphism. And this is important, otherwise this doesn't work. Okay, and because this metric is invariant with respect to volume preserving diffeomorphism, it induces a metric down on the space of probability densities. And that metric is often called the Otto metric or the Wasserstein-Otto metric. And the nice thing with it is that the distance induced by this metric is actually the Wasserstein distance, the L2 Wasserstein distance is important as well, of course. Okay. And this also means that we turn this principal bundle into Riemannian submersion. So we have this whole thing with horizontal geodesics and so on. There's a correspondence between horizontal geodesics on diffeomorphisms and geodesics on density space. Okay. Yeah, so this has implications for these Newton's equations that we're studying, because it means that we will always have so-called horizontal geodesics somehow, and normally what these horizontal geodesics correspond to are what is called potential solutions in fluid dynamics. I'll come to that later. And also, because now you see clearly because of this result here that the invariant potential function induces a function on the probability densities. So that's the one called U bar. Okay, there is also another point of view. So now I go from Riemannian geometry to symplectic geometry. So you can think of this as a sort of symplectic reduction. And for those of you who know a little bit about symplectic reduction, what happens now is we're working on the Hamiltonian side. So we're on the cotangent bundle of our diffeomorphism. And you have to be, when you do the analysis here, you have to be very, very careful to say what you mean with the cotangent bundle, but I won't get into that. So the first step is that you start with some Hamiltonian system on the cotangent bundle of your diffeomorphism, and you do what is called Poisson reduction. And in this case, this gives you a Poisson manifold, which is just the product between probability densities and the dual of smooth vector fields. And you can think of them as for example, one forms or something like that. And then once you have that, because now we're on a Poisson manifold, and you might know that Poisson manifolds, they are foliated into symplectic manifolds, and we look at one specific symplectic leaf in this Poisson manifold, and that actually corresponds to the cotangent bundle of the probability densities. So this is the second step that is often called symplectic reduction. And if we now go back to our Newton equations and we try to write them down as Hamiltonian systems, we can do that. And this is how it looks like after you do the Poisson reduction. So you have now two variables. You have your rho, which is your density, defining your probability density. And then you have your vector field u. And the equations for Newton's equation then will look like this. But after the symplectic reduction, so this is the correspondence, as I said. After the symplectic reduction, you get the system on the cotangent bundle of your probability densities, and that equation is very, very similar. It's some sort of Hamilton-Jacobi type equation. So the variable rho is now the base point on your cotangent bundle, and then the corresponding momentum variable, I call it theta. And I call it theta because I want to think of it as an angle. You will see why later on. So this theta variable is defined up to constants. That's important as well. Okay. So here is the first example, and this has been known for some time. So you just take your u bar of rho to equal the integral over some function e of rho times rho itself, integrated with respect to rho. So by the way, there are two different rows here, right? The curly one is the one that corresponds to the volume form. The other one is just the function that defines the density of the probability. Okay. So if you do this and you plug it into your framework, you get just the compressible Euler equations, so barotropic to be more specific, Euler equations. And P here is now what is called the pressure function in physics. So this is a nice example. And because it has this nice geometric interpretation, or it can be put into this geometric framework, we know already that there exist special solutions, the horizontal solutions. And these type of solutions is when the vector field is the potential of some function, is the gradient of some function. And they are called potential solutions, usually. But for our sake, we might as well just call them horizontal solutions. The other example still has been known for quite a while, but maybe it's new to more of you, and it's very, very interesting. It's the Schrödinger equations. So now we take our potential function to be first something that is similar to just the compressible Euler equations. F is just a function of some real variable. And then you add something, which looks like this. And this is nothing but the Fisher functional for our density rho. Okay. What's next? Well, now we can write down the equations. You see they look the same. I'm only interested in horizontal solutions now, by the way. So now I write down the equations on the cotangent bundle of the densities, and you see it looks the same, except we get this extra term here. F is just the derivative of capital F. Okay. So that's nice, but now let's take these variables and construct a wave function from them. So we construct the wave function in this way. We take the square root of rho times e to the power I theta, and this is why I think of theta as an angle, of course. And the square root of the whole thing, complex square root. And this is called the Madelung transform, or is very related to what is called the Madelung transform. And the nice thing is that if you do this, and you look at the equation that your wave function will fulfill, it's nothing but the nonlinear Schrödinger equation. So this is it gives you a connection between hydrodynamics and Schrödinger equations. And this was known already to Madelung right at the birth of quantum mechanics in 1927. And later years, people have sort of tried to understand this from a more geometric point of view. That's also what we've been trying to do, to sort of study this Madelung transform and understand what are the geometric properties of this mapping. And so far, the geometry, the Riemannian geometry I've been using, is the one that comes from the Otto metric, so the Wasserstein-Otto geometry. It turns out that that is not exactly the nicest one to use to understand the Madelung transform. So let's get into that. The first result is that you can think of this Madelung transform as a symplectomorphism. So, and to do that, you need to think of quantum mechanics in the geometric sense of Kibble. So here we think of wave functions as elements in an infinite dimensional complex projective space. Okay, that just means we sort of take away the phase, and when we assume that let's say that they have probability 1, so that they integrate to 1. And such a complex projective space, of course, it comes with a lot of structure. It's a Kähler manifold, so it's almost the best structure you have. You have both a symplectic structure and a compatible Riemannian structure with it. And the theorem is that the Madelung transform induces a symplectomorphism from the cotangent bundle of probability densities to an open subset of this complex projective space. And when I say open here, I mean it's in Fréchet topology of smooth functions, but those are just details. So that's very nice. But there is more. Because I said complex projective space has a Kähler structure. What about a Kähler structure on the cotangent bundle of probability densities? So we should be able to find that as well, and of course it's possible. And to do that, you get the connection to Fischer-Rao. So we start with a Riemannian metric, a canonical Riemannian metric on the space of densities. That's the Fischer-Rao metric. It's unique, it's the only one. that is fully invariant. Okay. And then, but we want a metric not on densities, but on the cotangent space of densities. So then we take this metric and we lift it in a certain way. This is sometimes called the Sasaki metric. So we get what is called the Sasaki-Fisher-Rao metric, and it looks like this. So this is in a Riemannian tensor. So at each base point, rho and theta, this is the inner product you're using. This is also going to be an invariant metric. It's not unique. It's obvious to see that it's not unique, but nevertheless, it's the most natural one, I think. And the result is that the Madelung transform is a Kähler morphism between the same two spaces. So, okay, so this is very nice. Okay, good, thanks. This is very nice because it gives us a way to sort of relate Kähler geometry or geometry in complex projective space to sort of hydrodynamic equations. Because I forgot to say that also there is a metric on the space of diffeomorphisms that sort of corresponds to the Fisher-Rao metric. It's not going to be an L2 metric, it's going to be H1 type metric, but you can also define that. So you get the connection to fluid dynamics here again. Some consequences of this. Well, as I said, you get a nice link between classical information geometry, where you study the Fisher-Rao metric, and quantum information geometry, where you study the Fubini study metric, or in physics they call it the Bourrier metric, and also hydrodynamics. So that's the first thing. But what is more interesting is that if you use this framework and try to sort of fit it to various type of equations, you get new understandings of several different types of PDEs. So here I mentioned the two-component Kamasa-Holm equation, the vortex filament flow. And then the last thing here, which I think is the most promising and most interesting thing, is that you get a way to think of relativistic quantum mechanics. You get a connection between relativistic quantum mechanics and hydrodynamics. So there is a way to think of the Klein-Gordon equation, which let's say is the simplest possible relativistic quantum equation. To think of this as a stationary solution to an infinite dimensional Neumann problem on Minkowski space. Okay, there's a lot of words here, but anyway, it fits quite nicely into this framework. So it gives us a new sort of geometric tools to study these kind of equations. Yeah, more to come, I hope. Thanks, that's all I had to say.
We have some time for one quick question.
So thank you for this very nice talk. Can you come back to the slide where you define the Sasaki-Fisher-Rao metric? Okay, so is there a typo? Should it be theta dot squared?
Yes, theta dot.
And so it's a cone metric actually. So so what's the link with a simple cone metric? Because if you take the square root, change a variable, then you get a sort of cone metric.
Yeah. So
right?
so this has explicit geodesics. That's what you're asking. Or?
In fact, my question is, why do you call it Sasaki-Fisher-Rao?
I mean, because that's the one that's the one that corresponds to the Fubini study metric. That's the reason.
And Sasaki, why Sasaki actually?
Because it's a lifted metric.
Uh-huh.
Right. But it's not unique, as I said, right? But this is the one that gives you Fubini study.
Okay, thank you.
So what is the complex structure you have on the T-star of densities? Or is a symplectic form exactly the canonical symplectic form on the contingent space? Or?
Yeah, good question. I didn't mention that. But of course, the symplectic structure is just the canonical symplectic structure of a cotangent bundle, right? And as I said, the metric structure is the one I showed you, the Sasaki-Fisher-Rao. And now you have 2 out of 3, right? So then you can work out the complex structure if you like. Yeah. Yeah, you can write it down, I'm sure. Yeah, yeah.
You don't have a physical meaning of it.
Of the complex structure? I never thought about that, no.
Yeah. So could you please repeat why this Otto Renesse view on the Madelung fluid may not be like the best one or the more convenient one?
Yeah, so in order to understand the Madelung transform as a Kähler morphism, you cannot use the Otto metric. So of course, if you're just interested in the symplectomorphism structure, then yes, you can add whatever metric you want, right? Because there's no sort of the metric structure and the symplectic structure, they don't speak to each other. But if you want to understand this in the nicest setting, you know, of Kähler geometry, you cannot use the Otto metric. That's not the one that you get actually.
So for instance, sometimes something which is really nice about this Otto structure is that by doing calculation as if it was an OD, you get some very nice quantitative properties about the evolution of, for instance, the Madelung fluid in this case. But as far as I know, for the Renesse representation, you cannot do that. There are some obstacles. Can you kind of overcome them with this new way of...
Which are the obstacles, did you say again?
For instance, you would like to show that the entropy is concave or convex along the Madelung fluid, the Shannon entropy. But somehow, as far as I know, you cannot do that in the specific case of the Madelung fluid. And I was wondering if maybe you can go a bit further in this direction and say something.
Yeah, so I haven't... So I've done this in the classical sense, so on the level of just a Fischer-Rao, not Sasaki Fischer-Rao. And of course there it works out perfectly nice, you know, with convexity of entropy, if that's what you're asking. I would...
No, but okay, maybe
we can discuss later, yeah.
A quick last question.
Just a remark on your abstract, you write this geometric setting for the Madelung transform shed light on the relation between the classical Fischer-Rao metric and its quantum counterpart, the Burr metric. But the Burr metric is not the quantum equivalent of the Fischer-Rao metric.
Well, in this sense it is.
Okay.
You see, so what is the connection between the Burr metric and
it has been presented by Roger Ballian in GSI 2013. You have a paper published in a special issue in 2015. No, it's not the Burr metric. So I could send you the paper, but
it's correct. The Fischer-Rao is not the Burr metric. But Sasaki Fischer-Rao is the Burr metric. That is my statement.
Okay.
And Sasaki Fischer-Rao is very related to Fischer-Rao. It's just a lifted version of that metric.
Okay, we can thanks again to the speaker and